Assalamu alaikum and good afternoon. I'm Saad Adnan. Today I will present an effective binary equilibrium optimizer based on fitness distance balance for the minimum k dominating set problem. Uh, my presentation will be give an introduction, then a background, then the formulation of the problem, then the proposed method, then the experimental setup, and results. Finally, the conclusion and some of the future work. The graph domination is a fundamental concept in the graph theory, which has various applications in network design, resource allocation, facility allocation problem, and influence maximization. In fact, the most application in influence maximization were choosing the dominating nodes as influencers to influence the remaining part of the network. This the challenge is the complexity of the problem, as it is an NP-hard problem which require intensive computation for large graph instances. Our contribution is the novel binary equilibrium optimizer and the integration of fitness distance balance, which improve the convergence and improve the performance of the algorithm. There are methods like the exact methods that used for the domination, including the branch and cat, branch and bound, and the integer linear programming. However, these algorithms are not scalable for large graph instances, and the greedy algorithms, even I didn't include here, which approximate the size of the minimum k dominating sets. However, these deteriorate with the size of the graph, and the meta heuristic algorithms, which are most frequently used for such problems, including the restart local set, genetic algorithm, simulated NEM, which used for different variants of the dominating set problems. Most algorithms in this field focus on intensification, search intensification. Limited work has focused on the solution diversity for the Mkds problem, and thus we try to use the fitness distance here for the diversity purpose. The problem formula definition for a given graph. For the dominating sets or the minimum k dominating sets is a subset of the graph where every other vertex in the graph are connected to at least k nodes in this set. For example, this graph here, 8 nodes here, and the shaded nodes are the dominating nodes, the k dominating nodes. To represent this graph, we use a binary representation, as we see here. The ones here represent the dominating nodes. Zeros are the other nodes in the graph. The main goal is to minimize the number of the dominating nodes, k dominating sets, which is calculated here. We use g-axis to count the number of nodes in the solutions. However, it has to satisfy the constraint here, which is every nodes must be connected to at least k nodes in the dominating nodes. We use this penalty calculation to penalize our solution, our fitness function. Here is the penalty coefficient. We calculate the number of nodes, the neighbors of each node in the dominating nodes, which is here expressed by sigma v. So if the solution is if the nodes is dominated by more than k, so it will be negative and the result will be 0. So there is no penalty. Otherwise, there will be a penalty. It requires to set the value of the coefficient, which the coefficient depends on the violation rate, which is counted how many nodes are not dominated. And the initial penalty coefficient, we set this experimentally. We try to optimize this parameter here. The advantage of our penalty coefficient. It prevents the HX, which is the penalty, from overwhelming the fitness function, which gradually move the solution towards feasibility and maintain the search maintaining the search process while the penalization is or the constraint is always satisfied. Uh, it works for different graph instances across different graph instances. The algorithm or the applied algorithm here, the binary equilibrium optimizer, it is inspired from physics. It is a meta-heuristic algorithm that mimics the mass balance at dynamic equilibrium, moving each solution toward a set of good candidates. uh, these candidates, they call it pool of solution. These candidates depend on, in the original algorithm, depend on the fitness value of each solution only. However, in this work, we adapted to fitness distance balance, which promote solution diversity. The position update of the solution, it here use a solution selected from the equilibrium pool, and then we convert it to a binary solution because this is a continuous continuous values. We convert it to binary using a sigmoid function. The fitness distance, it balances the quality, solution quality and diversity to prevent premature convergence. The calculation is the fitness of the for the FDB is the fitness of the solutions divided by the distance from the best solution. As we see here, it is a Hamming distance, which this enhances the exploration and avoid the local optima and more robust for different graph instances. For the experimental setup, we use different data sets, type 1 instances, which is used in the literature, and unit disk graphs, which is used to try to tune the initial value for the penalty coefficient. We apply the population size 50 individuals. We don't want to go beyond that because we want to manage the memory usage. And 1,000 iteration, also after 1,000 iteration there is no more improvement, so we usually stop at 1,000 iteration. And the penalty coefficient here is 8, is optimized, and the remaining parameter we use the standard parameter of the algorithm as used in the original paper. We compare to other methods like the restart local search, randomized greedy algorithm, and the standard binary equilibrium optimizer. For the K in this study, we use K minimum 2. So each node has to be dominated by at least 2 nodes from the dominating sets. And K max, which depends on the maximum degree of the graph divided by 2. So these standard values used in the literature. For 2, it's standard baseline. For K-max, test robustness and performance under most difficult feasibility conditions. For the penalty coefficient 8, it was the optimal value for all instances in the graphs. For the results, we just here present a snap of our results. For the most of the results for the graph instances, I either give same results, matching results for the remaining results, or improved some results. For small graph instances, match with other methods, existed one. And for the larger graphs, our algorithms outperform the remaining algorithms, outperform by 15 to 25 depending on the graph size. Our key contribution is the equilibrium optimizer with the FDB for the Mkds, handling the constraint of the Mkds problem, which give a superior performance and competitive results. Of course, the outcome of the FDB is better exploration and exploitation. reduce the prevention convergence and improved solution diversity and robust give a robust performance across different instances. For future work, we plan for parallelizing the using the GPU for acceleration and applying to weighted graphs and directed graphs as well. Thank you for listening. That's all. Uh, any question?